In this lecture, we will study the dominance relation, and we will first look at some basic facts about it and then show an inefficient and simple algorithm to compute this relation. And after that, we will see the standard algorithm, Lenga-Artarian, from 1979, which is what you will implement in lab 1. We will also see something called the dominator tree, which is a way to describe the dominance relation. And it's actually what Lenga-Artarian computes. Okay, so the definition of dominance. Recall from the previous lecture that U dominates V if U is on every path from start to V. And it's a reflexive relation, which means that a node dominates itself. I mean, it is on the path to itself. So, some notation. We write U dominates V like this. This is standard notation. And the set of all nodes which dominates W is written like this. So the dom S is contains only one element, and all vertices are dominated by S. Well, that's from previous knowledge. What we also need sometimes is that a node strictly dominates V. That means U dominates V and U and V are different. And we write that like this. We have a restriction on the control flow graph, namely that every node must be on a path from the start vertex to the exit vertex. So the first thing we do when we have constructed the control flow graph is to do a depth first search and remove all vertices which are not reached from the start vertex. Return statements, they are, as I mentioned in the previous lecture, they are collected in this special exit vertex. I mean, the expression in the in the return, it is obviously not copied to this, but the value computed in the return statement is returned in the exit vertex. There are also, I mean, there can be infinite loops, and they are not on the path from S to E to exit. Therefore, to fulfill that, we create a fake conditional branch to a suitable node in an infinite loop. And I mean, then it will be on a path to. So this fake conditional branch is always false and does not affect anything, and obviously will be removed during compilation and optimization. Okay. So some definitions, basic facts about sets and relations. You can pause and see that you remember this. What we will come to next is that dominance is a partial relation, which means it's reflexive, antisymmetric, and transitive. So we will see that. Next. First, that it's reflexive. Well, it's that means that the V dominates itself, and obviously it does, since it's on a path to itself. Dominance is also antisymmetric, which means that if both U and U dominates V and V dominates U, then they must be the same. Okay, so we will see that with a figure. Okay, so this is what I just mentioned, and now we will assume, we can assume that U is different from V, and consider a simple, that means cycle-free path from S to V. So this, and U comes before V since U dominates V. and it's different, so it's not the same. That's our assumption. But since V dominates U, it must be reached. I mean, we must reach it before we reach U. Okay, so this must be V. But now V is on this path twice, which means it's not cycle free, which means the assumption is false, which means U is equal to V. Okay, that dominance is transitive is also easy to see. Namely, if we have, well, first we say that U dominates V and V dominates W, and conclude that U dominates W. So how can we conclude that? Well, we start with arbitrary path from S to W. This path must contain V before reaching W, since, I mean, it can be the same, but we must reach V since V dominates W. Okay. Due to V is on this path, we must also reach U. So we can either U is equal to V or U is separate. We can put it as a separate. It doesn't matter. And now we can see that U is on this path to W as well. And this path was chosen arbitrarily, which means U dominates W according to the definition.